In this video, we'll look at understanding PCA code examples and understanding the concept of dimensionality reduction using some scientific computations. Okay, so I will be importing NumPy, Pandas, and Matplotlib for further purpose, for further procedure. So we'll be using a breast cancer dataset that we are going to import for sklearn for this task. So the dataset that we have will be in form of Python. So let's have a look on the keys of it. So we'll find we can see that data, target names, and description, feature name, and file name. These are the keys of our Python tag of our dataset. So what so we will be looking for data and the features name and the target for our data frame. So let's just have a glance over the data set that we have. Okay, so these are 30 columns, and looking at this, what we can observe is that all are the numeric values. Every column has numeric values, but the difference is that all different columns will have different ranges of different sets of ranges. For example, these are ranging something around 100, 70, 130, while these are just around 10, 17, and while these are around ranging over 1,300 and all 1,200, while these are just ranging around 0.1, 0.08, 0.1. So we can see that all columns have different sets of ranges. So the first step in PCA is that we set the ranges, we standard normalize them, we standard scalarize our distribution. What does standard scalarizing mean? It means that in a distribution of our data set, the mean of the distribution should be 0 and the standard deviation should be 1. Okay, so what is the so by having this we normalize our data, and our normalized data has has very low error. So our model fitting would be very well, and as we'll have less error probability, less possibility, so we can actually reduce the dimension very well. We can this won't create any bias towards our data or any towards any particular feature from our data set. So standard scalarizing is important part. So what I'll do, from sklearn preprocessing, import standard scalar, then I will fit transform the data set, the data frame, and we'll give it the name of scalar data. So let's just have a look at the shape of the scalar data. All right, it's 569 comma 30. Now the next step is that we'll find the covariance matrix. So how we find the covariance matrix from our sample data? So I have initiate sample data is equal to scalar data dot copy. All right, and then to find the covariance matrix, we'll need matrix multiplication. So for that I have used a numpy dot mat multiplication, matrix multiplication, np dot mat1. And what we'll do, how to find covariance matrix, then we'll by if we have matrix A, and if we multiply the transpose of matrix A with the matrix A itself, then we find the covariance matrix. So using this, I have coded covariance matrix is equal to np.mat1 sample data dot transpose into sample data, and we can find the shape of covariance matrix is equal to 30 cross 30. All right, now there is important step. So for this we'll be using SciPy library. SciPy library is a library which is mainly used for scientific computations. So right now what I'll do, I would from scipy.linear I would import eigauge. So eigauge is a method which return the eigenvalues in ascending order. So it returns the eigenvalues of a particular covariance matrix, and we can further use and through this we can take the eigenvalues of our need. All right, so what I will do, values comma vector is equal to eigauge, and then covariance matrix and eigenvalues of eigenvalues with order 28 and 29. Now let us understand. So what I said was the eigauge function will return the eigenvalues in ascending order for covariance matrix. So this covariance matrix is of shape 30 cross 30. So it will have eigenvalues in order 0, 1, 2 until 29. Alright, as it has a shape of 30. So for having top two eigenvalues, the order of them would be 28 and 29. Okay, so that's why we have used 28 comma 29 over here. So now for further computations, we'll convert eigenvectors into 2 comma dimension shape, because it will just create easiness for our further calculations. All right, so let's just have look on the updated shape of eigenvectors. So it's now 2 comma 30. All right, now to find our new coordinates, what I will do, I will have matrix multiplication of our vectors and the transpose of sample data. Remember, we took the transpose of vectors that we find using eigenvalue. So this our new vectors is actually the transpose of vector what we obtain from eigenvalue function. So our new coordinates would be matrix multiplication of vectors and the sample data, the transpose of sample data that we were using. So this is how what we are doing. We are just projecting the original data sample on the plane. Alright. So now with some matrix knowledge, with some matrix multiplication knowledge, we can see that the shape of vector is 2 cross 30. The shape of our data samples was 30 cross 569. The transpose of sample data was 30 cross 569. So when we multiply, so our output shape is 2 cross 569. We should have similar values of this, and these two are just eliminated, and whatever is left is our new output shape according to the matrix multiplication. Alright, so our new shape would be 2 cross 569. So now now we have obtained our reduced dimensions, and now we can see that as we had 569 data records and now we have two features corresponding to them. So if I have to create a new data frame, then I would take new chords dot transpose, because for pandas the shape should be in the form of 569 comma 2, and we'll give them names of column PC1 and PC2. So what this PC1 and PC2 is? Just principal component 1, principal component 2. Let's have a look over our new data frame. Right, so you can see that we have a PC1 and PC2 features, and then we have corresponding label. So this is how we converted 30 features into 2 features, and now we can easily perform any machine learning algorithm over it. So this is how we see that how using some scientific computations, how using some calculations and all, we can find a principal component axis, principal component corresponding to our need. Number of principal components we need, we will use take accordingly eigen values. So we needed to, that's why we took order 28 and 29. 28 and 29 are top two eigenvalues, because this function returns the eigenvalues in ascending order. So the top two eigenvalues would be on order 28 and 29. If we needed top three eigenvalues, then it would be 27, 28 and 29. So this is how we converted 30 features into 2 features using a PCA method. Now let us have just look over PC with scikit-learn. This becomes very easy if we use scikit-learn. So what we have to do, from sklearn.decomposition, we'll import PCA, then we'll instantiate PCA and have the number of components to be used. So we have been going through with 2 components, then I will use 2 here, and then I just xPCA is equal to PCA dot feed transpose our scalar data. So look at the important thing is that here also we'll need the scalar data. So with these 3 steps, our work will be done. So now you can see the scalar data and shape, and XPCA with its shape. So let me show you XPCA. So yeah, you can see that it's an array, and with each array it has two features. Alright, so it has two features for each array. Now, let me use matplotlib and show you some visualization. So what I'm doing, I'm plotting a scatter plot with XPCA and having in the XPCA and XPCA's index 0 and XPCA's index 1 as coordinates. So these are coordinates, these are again coordinates, and with datasets target as our labels, and will plot first principal component and second principal component, and accordingly the labels and scatter plot for that. Alright, so you can see that this is a different label, this is a different label, and using two principal component lines we have plotted them. And as you can easily see that now, to predict the labels it would be very easy task, because if you use any linear regression or logistic regression, then the line would go through this. We can also use KNN, and using any machine learning algorithm now further we can get a good accuracy over it, over the scale data. Okay, so as we have reduced the dimensions very well and running any machine learning algorithm, we can get a very good accuracy. So dimension reduction, so this was basically the part of data preprocessing, and we use PC algorithm for reducing dimensions. So now as if we have two features and a target column from our data set, now we can apply anything over it like train, test plate, or validation, or any type of method you want, and then fitting the model, and we'll get the accuracy. So this is how you can implement PCA with scikit-learn, or you can implement PCA with the scientific computation, some matrix multiplication method. Eventually we'll get good accuracy. The pre-processing task would be much easier, the model fitting would be much easier with this pre-processing.